This is your instructor, Richard Collins. Welcome to The Atmosphere, Unit 3 of ATM 101, Weather and Climate of Alaska. This unit explores two topics, the nature and composition of the atmosphere, and UPIC understanding of weather and climate. The unit's learning outcomes are to describe the basic structure of the atmosphere, explain how the composition of the atmosphere can change, interpret impacts of changes in the atmosphere on the Earth, compare different cultural approaches to understanding weather, and extend experience in observations and data analysis. This lecture supplements our textbook, Weather, A Concise Introduction by Gregory Hakim and Jerome Patou, and draws on the book Elavut, Our Yupik World and Weather by Anne Feinup Reardon and Alice Reardon. The atmosphere is an incredibly thin layer of gases that surrounds the Earth and is held in place by the Earth's gravity. 99% of the mass of the atmosphere is found at altitudes below 30 kilometers, while the Earth has a radius of about 6,400 kilometers. So the ratio of the atmospheric thickness to the Earth radius is 1 in 200. The sphere and arc on the slide show the relative size of the Earth and thickness of our atmosphere. The view from space shows the atmosphere as a thin blue layer lying on the horizon. While atmospheric motion is primarily horizontal, vertical motion is required to create the weather, and we will explore this much more in this semester. Mid-latitude storms extend further horizontally, about 500 kilometers than they do vertically, 10 kilometers, with an aspect ratio of 50:1. The atmosphere is made up of a mixture of gases, primarily molecular nitrogen, 78%, and molecular oxygen, 21%. But the nitrogen and oxygen molecules are each made up of 2 nitrogen and oxygen atoms, respectively. The atomic gases, argon, helium, and neon, add up to an extra 0.90025%. These gases are called the permanent gases, as their concentrations in dry air remain fixed across time and location in the atmosphere below 80 kilometers or 50 miles. The variable gases, water vapor, H2O, carbon dioxide, CO2, methane, CH4, nitrous oxide, N2O, and ozone, O3, vary in time and location. Water vapor varies dramatically, the air being most humid over the ocean, and the ocean serves as a source of moisture. Methane, found in highest concentration near its sources, natural gas reserves, swamps, rice paddies, and livestock. In the Arctic, there is concern that large amount of methane will be released from thawing permafrost. Nitrous oxide is released by plants and relatively inert in the troposphere, but becomes chemically active in the stratosphere. Ozone is formed by sunlight reacting with molecular oxygen. While ozone is a harmful pollutant in the troposphere, it serves as an ultraviolet shield in the stratosphere. These variable gases appear as small concentrations, but have significant impacts on the environment, and therefore are considered as being well able to punch above their weight. The gases in the atmosphere undergo cycles where the individual molecules of a particular compound are constantly being transferred to other compounds and back again. The cycles can be rapid, taking hours to days, or slow, taking years to millennia. Carbon dioxide is absorbed by plants through transpiration, where they produce oxygen. Carbon dioxide is generated by animals through respiration, where they absorb oxygen. Thus, we could have a balance between plants and animals as the carbon dioxide cycles back and forth between them. However, other sources of carbon dioxide include volcanic activity, agricultural fires, combustion of fossil fuels, decay of plants, and evaporation from the ocean. Other sinks of carbon dioxide include absorption by the ocean into seawater and absorption by sediments at the bottom of the ocean. Measurements of carbon dioxide have been made at Maui, Hawaii since the 1950s. Measurements in Hawaii are representative of the global background level, as the islands are located in the mid-Pacific, far from any industrial sources. We see that the concentration of carbon dioxide is a maximum in winter and a minimum in summer. This is because plants are less active in the winter, and so the production by animals outpaces absorption by plants. In summer, the absorption by plants outpaces the production by animals, and there is a minimum. Superimposed on this cycle is a steady increase due to burning of fossil fuels. This carbon is chemically tagged, as fossil fuels are formed by plants that have died a long time ago, and hence they have lower levels of carbon-14 than carbon from contemporary plants. The history of the Earth spans about 5 billion years when the planet formed in a swirl of gas, surviving an early meteor impact where enough debris was lost to form the Moon. The planet formed as we know it with an inner core, outer core, mantle, and crust. A magnetic field was formed by the liquid core, and eventually outgassing water vapor established an ocean. Life began, and oxygen began to form. Cyanobacteria began to create more oxygen, and increasing oxygen levels supported more complex life. During this period, there was a cooling period where the planet froze and there was a snowball Earth. This snowball was formed as more ice reflects more sunlight, yielding more cooling and more ice formation, an example of positive feedback. However, plate tectonics continued and eventually liberated enough carbon dioxide to support an increase in greenhouse. Furthermore, wind-blown dust darkened the surface and absorbed heat, contributing to the warming. With further increased oxygen, an ozone layer formed. A 12-point history of the atmosphere. About 13.8 billion years ago, the universe forms. About 4.6 billion years ago, the Earth and Moon form. About 4.5 billion years ago, Earth's first atmosphere forms from solar system gases and is short-lived. These gases include hydrogen and helium. 4.4 billion years ago, Earth's second atmosphere forms from outgassing. These gases include ammonia, carbon dioxide, methane, nitrogen, and water vapor. Nitrogen comes to dominate the atmosphere. About 2.4 billion years ago, oxygen increases. About 2 billion years ago, oxygen-producing bacteria appear. About 0.7 billion years ago, carbon dioxide levels drop and snowball Earth forms. Eventually, the snowball melts as carbon dioxide levels increase, and this is followed by the Cambrian explosion about 0.5 billion years ago, when there is a massive increase in the diversity and distribution of life on Earth. About 0.5 billion years ago, modern oxygen levels are reached, and this represents the establishment of Earth's third atmosphere, the atmosphere that we have today. About 0.5 billion years ago, the oxygen atmosphere also produces an ozone layer, which also contributes to promoting life on Earth. About 200,000 years ago, humans finally appear, and 200 years ago, carbon dioxide levels begin to rise rapidly on Earth. Unlike our neighbors Venus and Mars, Earth is remarkably habitable. What made Earth habitable? The first point is that Earth's temperature supports unfrozen oceans, and oceans can store carbon, they can incubate life, and they act as a thermal and chemical buffer on climate change. 2. The distance from the Sun and the planetary gravity allows most, but not all, hydrogen to escape. 3. Active plate tectonics renew the atmosphere. And so, for example, during the snowball Earth period, the plate tectonics allowed for the release of greenhouse gases into the atmosphere, ending the snowball. 4. An active hydrological cycle sustains life on Earth. 5. Massive outer planets, such as Jupiter and Saturn, deflect comets from Earth's orbit and reduce the amount of cometary bombardment of the Earth. 6. The strong gravitational pull of the Moon reduces the obliquity of the Earth and therefore reduces the severity of the seasons. And finally, 7. The Earth's rotation rate supports a reasonable day-night cycle. Ozone is part of the natural chemistry of oxygen in the atmosphere. Ozone is in a natural chemical cycle where it absorbs ultraviolet light as oxygen atoms, O, that cycle between molecular oxygen O2 and ozone O3. Humans released chlorofluorocarbons into the atmosphere in the 20th century, and these chlorofluorocarbons were a source of free chlorine in the stratosphere. That free chlorine was able to catalytically destroy ozone. When the ozone hole first appeared, it was quite a surprise, and the first evidence was ignored. However, once the ozone hole was discovered and the causes of it established, the Montreal Protocol was established that banned CFCs in 1989 and led to the recovery of the ozone layer in the 2010s. The ozone hole was first reported from Antarctica by Joe Farman and his colleagues. The hole appears as a thinning of the ozone over Antarctica and appears in the satellite maps as the blue minimum that is surrounded by the higher levels of ozone in green and yellow. And you can see that the hole covers the whole of the Antarctic continent. The scientific efforts to understand the ozone hole were led by Susan Solomon, who determined that the loss was due to the accumulation of chlorine-bearing compounds in the stratosphere. The compounds known as CFCs were widely used in refrigeration and industrial processes. The discovery led to the ban of CFCs in the Montreal Protocols. Thus, the hole appears in the late 1970s, is discovered in the mid-1980s, the Montreal Protocol is implemented in the late 1980s, and the ozone layer begins to recover in the 2010s. In 1989-1990, I spent a year at the South Pole making measurements of the clouds that are instrumental in the formation of the ozone hole. My measurements show that the altitudes where most ozone was lost correspond to those altitudes where the clouds are thickest. The South Pole station is shown next to Drs. Farman and Solomon. For working at the South Pole for a year, I got the measurements for my PhD and a medal from the US Navy. As we move vertically through the atmosphere, the temperature falls, rises, falls, and rises again. In contrast, the density and pressure fall steadily. In the layer closest to the ground, the temperature falls with altitude, and the atmospheric motions allow the air to turn over. Hence, the region is called the turning sphere or troposphere. About 10 kilometers or at 200 hectopascals, there is a local minimum in the temperature before it begins to increase again. This marks the top of the troposphere, called the tropopause. We are now in the stratosphere, where the atmosphere is stratified or layered. The temperature rises with altitude, called an inversion, up to 50 kilometers, corresponding to a pressure of 1 hectopascal. This increase in temperature is due to heating of ozone by absorption of ultraviolet light. The temperature reaches a maximum at the stratopause before decreasing with height in the middle or mesosphere. Eventually, we reach a minimum at the mesopause, about 80 kilometers or 0.01 hectopascal. This is the region where meteors or shooting stars burn up in the atmosphere. The temperature then increases in the thermosphere. Here, due to absorption of hard ultraviolet light and the sparseness of the gas, the molecules and atoms achieve very high speeds and have very high temperatures. The ionosphere is the region above 60 kilometers where a significant number of atoms and molecules are ionized. This charged region of the atmosphere is called the ionosphere, and it significantly impacts communication and navigation systems. The aurora occurs in the ionosphere. So just to recap, we have the troposphere as the lowest layer where temperature decreases with altitude. It has the most water vapor, most weather, most clouds, and it has the jet streams. The stratosphere is where the temperature increases with altitude, there's a temperature inversion, and the ozone layer is found in the stratosphere. Then in the mesosphere, the temperature again decreases with altitude, ozone is decreasing through this region, and this is the region where shooting stars and meteors come into the atmosphere and are visible from the ground, burning up at the height of the mesopause. The thermosphere is where the temperature increases with altitude, the gas becomes very hot and very sparse, and this is the altitude where the aurora occurs. Finally, the ionosphere is a layer of charged atoms, ions, and free electrons. It extends from about 80 kilometers to 600 kilometers, and the ionized particles and electrons impact radio waves and communication. We now discuss Yupik ways of understanding weather and climate. About 22,000 Yupik people live in southwest Alaska around the Yukon-Kuskokwim Delta. Bethel, Mumterriluk, a city of 7,000 people, is the capital of the Yupik region. The Yukon-Kuskokwim Delta is in the west coast climate region of Alaska, and the climate is more moderate and wetter than that of the interior. The interior has warm summers and cold winters, with high monthly temperature in July of nearly 15 degrees Celsius and low temperatures in January of minus 25 degrees Celsius, for an annual range of 40 degrees Celsius. The West Coast has a summer high of about 12 degrees Celsius and a winter minimum of about minus 20 degrees Celsius for an annual temperature range of 30 degrees Celsius. There is more precipitation in Bethel, with higher precipitation in spring and early summer. Both sites show a maximum in precipitation in late summer and early fall. The Yupik word Ella translates as weather, world, universe, and awareness. In modern times, it has taken the meaning atmosphere, environment, and climate. Anne Feinup Reardon and Alice Reardon engaged in a consultation and listening with Yupik elders of the Callista Elders Council to understand how Yupik people understand their world and weather. Elders and youth gatherings resulting in discussions and dialogue rather than traditional anthropological interviews. Elders including Mark John, David Jimmy Sr., David Shanar, and John Eric attended these sessions. The Yupik Native Corporation, Callista, recognized the importance of this work through the Callista Education and Culture Incorporated. CC Cultural Advisor Mark John is seen at an award ceremony for writers Anne Feinup Reardon, Mary Mead, and Alice Reardon. Yupik people recognize 1. That the weather is not random, but can be forecast, and Ella does not try to surprise people. Ella only requires that people are observant. 2. They recognize that gaining expertise requires immersion in a topic. Children are encouraged from a young age to watch the sky and recognize the behavior of the weather. And 3. That using optical phenomena to forecast the weather is place-specific. For example, superior mirages or Inikak indicate bad weather in the Yukon-Kuskokwim Delta, but indicate calm conditions in the Tanana Valley in the interior. Unit 3 Summary and Takeaways. The atmosphere is composed of permanent gases whose proportions are constant up to 80 kilometers or 50 miles. These are nitrogen, oxygen, argon, neon, and helium. Variable gases can vary in concentration dramatically over time and space. These include water vapor, carbon dioxide, methane, nitrous oxide, and ozone. Aerosols are also found in the atmosphere. These are small liquid and solid particles that include soil particles, bacteria, smoke, industrial exhaust, and other particles. The composition of the atmosphere has varied in the past and will continue to change in the future. Gases continually undergo cycles rather than remain static in the atmosphere. Atmospheric density and pressure decrease with altitude, while temperature increases and decreases in different regions or spheres with distinct meteorological characteristics. And finally, Yupik people have developed methods of weather forecasting that are based on systematic understanding, observational experience, and recognizing how optical patterns vary with geography.